What if everything you thought you knew about space and time was only half the story? Picture this: the fabric of reality isn't just a static stage where events unfold, but a dynamic, living thing that twists, bends, and even dances with itself. This isn't science fiction. It's the frontier of modern physics, where the dual nature of space and time reveals mysteries so profound, they'll make you question the very ground beneath your feet. From the way black holes warp the universe to the strange quantum connections that defy distance, these aren't just abstract ideas, they're clues to understanding the deepest layers of existence. And today, we're diving into 30 of the most astonishing theories that reveal how space and time are far more mysterious, more interconnected, and more alive than we ever imagined. Think about the last time you looked up at the night sky. Those stars aren't just distant points of light, they're glimpses into the past, their light traveling millions of years just to reach your eyes. But what if time isn't the steady river we assume it to be? What if it's more like a swirling vortex where the past, present, and future tangle together in ways that defy logic? Einstein's theory of relativity shattered our old ideas, showing us that time slows down near massive objects and speeds up in empty space. But that was just the beginning. Today, physicists are uncovering even wilder possibilities like parallel universes where time flows backward, or dimensions curled up so tightly they're hidden in plain sight. These aren't just thought experiments, they're real theories backed by math and observation, pushing the boundaries of what we thought possible. So why does any of this matter to you? Because the nature of space and time isn't just a puzzle for scientists, it's the foundation of reality itself. Every second you experience, every step you take, is part of this grand cosmic dance. Understanding these theories doesn't just expand your mind, it changes how you see the world. It's the difference between living on the surface of things and peering into the depths where the universe reveals its secrets. Over the next few minutes, we'll explore ideas that will stretch your imagination, from wormholes that could connect distant corners of the cosmos to the mind-blowing concept that time might not even exist at the most fundamental level. This isn't just a journey through physics, it's an adventure into the unknown, and you're right at the edge of discovery. So take a deep breath. Reality is about to get a whole lot stranger. The block universe theory isn't just a wild thought experiment, it's a radical reimagining of reality itself. Imagine every moment that ever was or ever will be, stacked together like pages in an infinite book. Your birth, your first steps, even the words you're hearing right now, all fixed in place like scenes in a movie already filmed. Einstein's equations hinted at this. Time isn't a flowing river but a frozen landscape, where now is just where your consciousness happens to be standing. It's as if the universe is a vast museum, and we're visitors walking through its halls, mistaking each exhibit for the present. But here's where it gets even stranger. If the future already exists in this block, does that mean our choices are illusions? Some physicists argue yes, that free will is just a trick of the mind, a story we tell ourselves to make sense of the inevitable. Others push back, suggesting that even in a predetermined universe, our decisions still matter because they're woven into the fabric of the whole. Think of it like reading a novel. Just because the ending is written doesn't make the journey any less real for the characters. And then there's the quantum twist. At the smallest scales, particles seem to defy the block universe, behaving as if multiple futures are possible until observed. Could this mean time is both fixed and fluid, like a river that's already reached the sea but still ripples with uncertainty? The debate rages on, bridging philosophy and physics in ways that challenge everything we thought we knew. One thing's certain: this theory doesn't just stretch the mind, it shatters the very idea of what it means to exist in time. Now, let's peel back another layer. If the block universe feels unsettling, wait until you hear about the holographic principle, a theory suggesting our three-dimensional reality might just be a projection of information stored on a distant, two-dimensional surface. It's not science fiction, it's a serious idea born from studying black holes, where the laws of physics twist into paradoxes. Picture a movie screen. The images appear deep and lifelike, but they're really just flat patterns of light. What if the universe works the same way? Every event, every particle, even your own thoughts, could they all be encoded on some cosmic boundary we can't see? This isn't just about rewriting textbooks, it's about redefining reality. If the holographic principle holds, space and time aren't fundamental but emergent, like waves rising from an unseen ocean. Suddenly, the solid ground beneath us feels more like a mirage, a trick of perspective. And here's the kicker: if true, it could mean the universe is far simpler and far weirder than we ever dreamed. Eternalism flips everything we think we know about time on its head. Imagine standing in a vast library where every book represents a different moment: your first birthday, the fall of ancient Rome, events centuries from now, all equally real, all sitting on the shelves at once. This isn't just a poetic metaphor, it's how some physicists and philosophers view reality. They argue that time isn't a parade of moments fading into oblivion, but a dimension where past, present, and future coexist, fixed and unchangeable, like landmarks on a map. Take time dilation, for example. When astronauts orbit Earth at high speeds or hover near a black hole, their clocks tick slower than ours down here. Eternalism explains this beautifully. Those astronauts aren't just moving through space differently, they're literally navigating a different slice of the timeless cosmic tapestry. Their now is just as real as ours, just stitched into the fabric at a different angle. It's as if the universe is a grand, four-dimensional sculpture, and we're only seeing one cross-section at a time. But here's the puzzle that keeps philosophers awake at night. If every moment is equally real, why does life feel like it's moving? Why do we remember the past but not the future? Some suggest that consciousness itself is the key, that our brains are like projectors, illuminating one frame of the eternal movie at a time. Others propose that change is an illusion, a trick of perspective, like mistaking a train's motion for the landscape rushing by. And then there's the quantum wrinkle. At the smallest scales, particles seem to dance outside of time, existing in superpositions until measured. Could this mean eternalism is incomplete, that time is both fixed and fluid, like a river frozen in ice yet still bubbling beneath the surface? The debate isn't just academic. If eternalism is true, it reshapes everything from how we understand history to whether our choices truly matter. After all, if the future is already out there, waiting to be discovered, does that make us explorers or just characters in a story we can't rewrite? This leads us to the next mind-bending idea: the growing block universe, a twist on eternalism that suggests the past and present are real, but the future is still unwritten. It's like watching a painting being made, each brushstroke fixed once applied, the blank canvas ahead still full of possibility. Could this be the bridge between a static universe and our lived experience of time's flow? The answer might lie in the strange, shimmering boundary where physics meets philosophy. The growing block theory offers a fascinating middle ground between the rigid block universe and our lived experience of time's relentless march forward. Picture reality as a vast, unfinished sculpture. Every passing second adds another layer of stone, expanding the structure while leaving the space ahead untouched and undefined. Unlike eternalism, which locks past, present, and future into place, This theory suggests only the past and present are concrete, while the future remains a blank canvas of possibility. It's as if the universe is writing its own biography, with each new chapter ink still wet, not yet dried into permanence. Arthur Eddington, one of the theory's early champions, saw this as a way to preserve both the objectivity of physics and our human sense of becoming. After all, when you make a choice whether to turn left or right, to speak or stay silent, it feels like you're shaping something genuinely new. The growing block universe agrees, treating your decisions not as illusions but as real stitches in the fabric of time. Think of it like a tree growing rings. Each year's growth is undeniable, but the next ring hasn't formed yet. But quantum mechanics throws a wrench into this elegant picture. At the subatomic level, particles don't follow predictable paths. They exist in clouds of probability until measured. If the future is truly open, does that mean it's governed by pure chance? Or could there be hidden layers of order we haven't uncovered? Some physicists argue that quantum randomness is proof the growing block is real, that the universe genuinely doesn't know what comes next. Others counter that even apparent randomness might be part of a deeper, unseen pattern, like waves crashing in ways that seem chaotic until you account for the tides. This isn't just philosophical sparring, the stakes are cosmic. If the growing block theory is correct, it means reality isn't just unfolding, it's accumulating moment by moment with genuine novelty emerging from the void. It's a vision that gives weight to our choices, our struggles, even our hopes, but it also raises a haunting question. If the future isn't written yet, what or who is doing the writing? The answer might lie in the next theory, where time doesn't just grow, it branches, splitting into infinite parallel streams. The multiverse hypothesis isn't just about alternate realities. It's a cosmic explosion of possibilities where every choice, every chance event, fractures existence into infinite new timelines. Picture standing at a crossroads where each path doesn't just represent a different future, but an entirely new universe springing into being. This is the heart of Hugh Everett's many worlds interpretation, where the strange behavior of quantum particles isn't a paradox but a doorway. Every time an electron could go left or right, every time you hesitate between two decisions, reality doesn't choose, it branches, creating parallel worlds where all outcomes play out. Think of it like flipping a coin. In our world, it lands heads, but somewhere in a universe almost identical to ours, it lands tails, and that tiny difference ripples outward, shaping entirely new histories. The implications are staggering. That job you didn't take, there's a version of you living it. The words you left unsaid, in another reality, they were spoken. The universe isn't a single story but an endless library, each book telling a different tale of what could have been. But here's the twist that bends the mind even further. If these parallel worlds exist, could they ever touch? Quantum physics hints at eerie connections between particles across vast distances. What if universes whisper to each other the same way? Some theories suggest faint gravitational echoes or quantum entanglement might leave traces, like shadows cast between dimensions. Others propose that black holes could be cosmic stitches, sewing different timelines together in ways we can't yet see. And then there's the haunting question. If every possibility happens somewhere, does that make our choices meaningless? Not necessarily. In the multiverse, your decisions still matter. They determine which branch you follow, which story you experience. It's like being the protagonist in a choose-your-own-adventure book where every ending exists, but you only get to live one. This brings us to the next theory, where the boundaries between worlds might not be walls but permeable membranes, and the fabric of reality itself could be more like a web, stretching, vibrating, and maybe, just maybe, trembling with echoes of the paths not taken. Entropic time turns our everyday experience of cause and effect into a cosmic detective story. Imagine walking into a room where a vase lies shattered on the floor. You instantly know what happened, not because you saw it fall, but because broken things don't spontaneously reassemble. This intuitive understanding is entropy in action, the universe's irreversible slide from order to disorder, giving time its unmistakable direction. But here's the twist: what we perceive as time's flow might just be a side effect of this cosmic messiness. The past hypothesis proposed by physicist Ludwig Boltzmann suggests the Big Bang handed us a universe in an improbably pristine, low entropy state, like a perfectly stacked deck of cards. Ever since, the deck's been shuffling itself, and that relentless mixing is what we call the passage of time. Now, picture a video of an exploding firework played in reverse. The sparks would rush inward, defying logic. Entropic time says reality works the same way. We remember the past, but not the future, because one direction fits entropy's narrative. But what if that narrative isn't universal? Some corners of physics flirt with the idea of entropy running backward. In a mirror universe where time flows opposite to ours, would beings there perceive our present as their distant past? The equations allow it, but reality seems to stubbornly resist. This leads to a haunting possibility. If entropy defines time's arrow, could a universe with maximum disorder, a state called heat-death, simply stop experiencing time altogether? It's like a clock submerged in molasses, each tick slower than the last until stillness reigns. Yet even here, nature surprises us. Quantum fluctuations might stir the cosmic soup, creating pockets where entropy temporarily dips, like eddies in a river. Could these eddies birth new arrows of time, new beginnings woven from the ashes of the old? The answer might lie in the next theory, where time isn't just a line or an arrow, but a branching tree with every quantum decision sprouting fresh timelines. And that's where things get really strange. If entropy can't fully explain time's grip on reality, perhaps we've been missing half the story, a hidden layer where time isn't just flowing but multiplying, fracturing into infinite parallel streams. The glass isn't just shattering in one universe, it's reassembling in another, and the distinction between past and future might be far more fluid than we ever imagined. The cyclic universe model shatters the idea of time as a one-way street, replacing it with an endless cosmic carousel where universes rise, fall, and are reborn in an infinite dance. Picture a pendulum swinging through the ages. Each arc represents a complete universe, from the fiery birth of a Big Bang to the slow fade of heat death, only to be pulled back into another explosion of creation. Roger Penrose's vision takes this even further. His conformal cyclic cosmology suggests that when our universe stretches into cold, empty darkness, its very geometry resets, scrunching down until it becomes indistinguishable from the seed of the next Big Bang. It's as if time itself hits a cosmic rewind button, not by reversing, but by folding its end back into its beginning, like an Ouroboros swallowing its tail. But here's the breathtaking twist. Black holes might be the universe's time capsules. Penrose theorizes that these gravitational monsters preserve traces of previous cycles, imprints of ancient universes etched into their Hawking radiation like messages in cosmic bottles. If true, the night sky isn't just a window into space, but into time beyond time, where echoes of forgotten realities linger at the edge of perception. Now consider what this means for the arrow of time. In each cycle, entropy resets, giving the new universe a fresh start, a clean slate where order emerges from chaos once again. But could something carry over? Could the laws of physics themselves evolve across cycles, tweaked slightly each time like a recipe passed down through generations? Some versions of the theory suggest just that, hinting at a grander meta-time where cycles aren't identical, but variations on a theme. Yet the most haunting question remains: if time is cyclical, are we destined to relive the same cosmic story, the same triumphs and tragedies over and over? Or does each cycle bring genuine novelty, a chance for the universe to reinvent itself? The answer might lie in the seventh theory, where time doesn't loop its splinters, branching into infinite parallel streams where every possibility plays out. Causal set theory turns the smooth, flowing fabric of spacetime into something far more radical, a universe built from tiny, indivisible moments, like grains of sand in an infinite hourglass. Imagine zooming in on a movie screen until you see the individual pixels. Reality, according to this theory, works the same way. Instead of the continuous spacetime Einstein described, the cosmos is a vast network of discrete events, each connected by cause and effect. Time isn't a river here, it's a chain reaction, with each link representing a fundamental atom of causality. Raphael Sorkin and other physicists champion this idea as a way to bridge the gap between quantum mechanics and gravity, two frameworks that have stubbornly resisted unification. But here's where it gets even more intriguing. If spacetime is pixelated, what does that mean for the smallest possible scales? Picture trying to measure the length of a coastline with a ruler. The closer you look, the more jagged and complex it becomes. Causal set theory suggests something similar. At the tiniest levels, the smooth geometry of spacetime shatters into a froth of causal relationships, where concepts like before and after are the only things that matter. There's no smooth continuum, no infinitesimal points, just a cosmic web of cause and effect, with each event dictating the next like dominoes falling in perfect sequence. This raises a profound question. If time emerges from the order of events, could there be regions of reality where causality breaks down? Some models hint at pockets where the chain of cause and effect tangles, creating loops or even islands of a causality, places where the past influences the future, and the future loops back to reshape the past. It's as if the universe itself has glitches, moments where the rules we take for granted simply don't apply. And then there's the quantum connection. In a pixelated universe, the weirdness of quantum mechanics particles being in multiple states until observed might not be a bug but a feature. If reality is fundamentally granular, then superposition could just be the system waiting for the next causal click to lock in a definitive outcome. Think of it like a cosmic game of chess, where each move is a discrete event, but the board itself is fluid until the pieces settle. This theory doesn't just challenge our understanding of spacetime, it redefines what it means for something to happen. If the universe is a causal set, then every moment, every decision is a node in an unimaginably vast network, with the arrow of time emerging from the pattern of connections. It's a vision of reality where the flow of time isn't an illusion, it's the deepest truth of all, written in the language of cause and effect. Now let's push further into the unknown. If spacetime is pixelated, what lies beyond the pixels? The eighth theory takes us to the edge of comprehension, where the fabric of reality itself might be woven from something even stranger, a sea of pure information waiting to be decoded. Loop quantum gravity rewrites the rules of reality with a radical proposition: spacetime isn't smooth or continuous, but a shimmering tapestry woven from tiny, vibrating loops. Imagine the universe as a cosmic quilt, each stitch a thread of pure energy called a spin network. These loops don't just sit there, they hum with activity, their interactions generating the very fabric of space and time. Unlike the infinite divisibility of classical physics, here the universe has a smallest possible scale, a granularity where space can't be split further, like trying to cut a piece of thread into smaller and smaller segments until you're left with a single, indivisible fiber. This theory tackles one of physics' biggest headaches, the singularity inside black holes. General relativity predicts a point of infinite density where space-time curves beyond comprehension. But loop quantum gravity says no, those infinities vanish because space itself is pixelated. Picture a digital photo blown up too far. Eventually, you see the pixels. In this model, black holes aren't bottomless pits but dense knots where spin networks tangle tightly, preventing the math from exploding into nonsense. Yet the real mystery lies in time. If space-time is quantized, why does it feel like it flows? Loop quantum gravity treats time as just another dimension, stitched into the cosmic quilt. But our experience of moments passing the urgency of a ticking clock, the weight of memories isn't easily explained. Some theorists suggest time's flow might emerge from the way these loops interact, like the illusion of movement in a flipbook. Others argue that now is a kind of cosmic consensus, a shared moment agreed upon by the spin networks in our local patch of reality. The implications stretch even further. If space and time are woven from loops, could the universe have a memory? Could traces of past events linger in the way these threads knot together? It's a haunting thought that the fabric of reality might bear scars from ancient cosmic collisions or whispers from the first moments after the Big Bang. This brings us to the ninth theory, where time isn't just quantized, it's an illusion, a side effect of something far deeper. If loop quantum gravity is the quilt, then the next idea pulls at its threads, unraveling time itself into something even more astonishing. The holographic principle doesn't just bend our understanding of reality, it shatters it entirely. Imagine stepping into a room filled with mirrors, only to realize the reflections aren't just images, they're you in some deeper, stranger way. That's the essence of this theory. Our three-dimensional universe, with its galaxies, planets, and even your own hands, might be nothing more than a projection of information etched onto a distant, two-dimensional surface. It's as if everything we experience, every sunrise, every whispered conversation, every heartbeat, is just a hologram, a cosmic illusion flickering into existence from data encoded on the edge of the unknown. Leonard Suskind's groundbreaking work with black holes planted the seed for this mind-blowing idea. When matter falls into a black hole, it doesn't just vanish, it leaves an imprint on the event horizon, like a fingerprint pressed into wet clay. The holographic principle takes this further, suggesting that all information in the universe might be stored this way, with our reality unfolding like a movie projected from the boundary of some unimaginable cosmic screen. Think of it like a credit card hologram, tilted, and the flat surface seems to contain depth. But what if the universe itself works the same way? And here's where time enters the equation. If reality is a hologram, then time might not be a fundamental force, just a side effect of how information updates on that distant surface. Picture a flipbook. The illusion of motion comes from flipping static pages. In the same way, our experience of time's flow could be the universe refreshing its data frame by frame on a boundary we can't see. This raises a haunting question. If time is just emergent, does that mean the past and future are equally real, just waiting to be played back? But not everyone's convinced. Critics argue that if the holographic principle is true, why does reality feel so solid? Why do we stub our toes on tables if they're just projections? Defenders counter that even illusions have rules. A rainbow is just light refracting, but its colors feel undeniably real. The debate isn't just academic, it's a battle over the nature of existence itself. This leads us to the 10th theory, where reality's illusions go even deeper. If the holographic principle makes our universe feel like a shadow, Wait until you hear what comes next, a realm where time isn't just emergent but optional, and the very fabric of existence might be rewriting itself in ways that defy all logic. Time crystals shatter everything we thought we knew about matter and motion. Picture a snowflake, but instead of its intricate pattern repeating in space, imagine a structure that repeats in time, cycling through its states like a cosmic metronome, forever ticking without energy or decay. This isn't fantasy, it's the brainchild of Nobel laureate Frank Wilczek, who dared to ask, could there be a phase of matter that breaks time's symmetry, dancing to its own eternal rhythm? The answer, it turns out, is yes, but the implications are even wilder than the theory itself. In ordinary crystals like diamonds or salt, atoms arrange themselves in repeating spatial patterns. Time crystals flip this idea on its head. Their atoms oscillate between configurations not because of external energy, but because the system falls into a quantum groove, a rhythm locked into the fabric of reality itself. Think of a pendulum that swings forever without being pushed, or a bell that rings perpetually without being struck. It defies the second law of thermodynamics, not by breaking it, but by sidestepping it entirely, a loophole in the universe's rulebook. The magic lies in quantum entanglement. In a time crystal, particles become so deeply linked that they synchronize their motion across time, creating a self-sustaining cycle. It's like a chorus of singers who, once started, never miss a beat, not because they're keeping time, but because their voices are inescapably tied together. Experiments with chains of ions or diamond defects have already glimpsed this eerie behavior, confirming that time crystals aren't just mathematical curiosities. They're real, and they're rewriting our understanding of equilibrium. But here's the breathtaking twist. If time crystals can persist indefinitely without energy input, could they be the key to a kind of quantum immortality? Not for living beings, of course, but for information. Imagine data storage that never degrades, or clocks that keep perfect time until the end of the universe. Even more tantalizing is the possibility that time crystals might reveal hidden layers of time structure, like echoes of a deeper physics we've yet to uncover. Yet for all their strangeness, time crystals don't violate the laws of thermodynamics. They're not perpetual motion machines in the classic sense. They're more like cosmic harmonies, resonating in a way that expends no energy. It's as if the universe composed a song that sings itself, a melody woven into the quantum fabric, playing on loop for eternity. This leads us to the 11th theory, where the fabric of reality gets even stranger. If time crystals hint at eternal rhythms, what happens when time itself becomes a fluid, shape-shifting entity? The answer lies in a realm where the past, present, and future aren't just connected, they're interchangeable. The Wheeler-DeWitt equation is where physics takes a hammer to our most basic intuition, the idea that time flows at all. Imagine writing the ultimate rulebook for the universe, a single equation that stitches together quantum mechanics and gravity, only to realize you've left out time entirely. That's exactly what physicists John Wheeler and Bryce DeWitt discovered in the 1960s. Their equation describes reality at the deepest levels with breathtaking elegance, but with one glaring omission: the variable t for time simply isn't there. It's as if the universe whispered a secret that time might not be fundamental, but something that emerges from a more basic, timeless reality. This revelation sends shockwaves through our understanding of existence. If time isn't baked into the fabric of the cosmos, why does life feel like a relentless march from past to future? One compelling answer comes from quantum entanglement. Think of reality as a vast, frozen landscape where every possible configuration exists simultaneously, like a cosmic film strip with every frame laid out at once. Our experience of time could be the result of quantum systems becoming entangled in a particular sequence, creating the illusion of a flowing now. It's akin to watching a movie. The frames are all there, but the projector's light makes them feel like motion. But here's where it gets even more radical. Without time as a fundamental ingredient, concepts like before and after lose their absolute meaning. The Wheeler-DeWitt equation treats the universe as a single, unchanging object, a block where every event is equally real, just viewed from different angles. This doesn't mean change is an illusion. It means change is relative, a perspective that arises from how we interact with the quantum tapestry. Imagine standing in a hall of mirrors. Your reflection moves when you do, but the mirrors themselves stay still. Time might work the same way, a dance of perception, not a feature of the stage. Critics argue this can't explain the visceral urgency of time's passage the way a deadline looms or a memory fades. Yet proponents counter that urgency itself could be emergent, like the wetness of water arising from molecules that aren't wet individually. If true, it means time isn't slipping away. We're just tracing paths through an eternal mosaic, mistaking our journey for the landscape. This leads us to the 12th theory, where the paradox deepens. If time isn't fundamental, why does it feel so inescapable? The answer might lie in a realm where time isn't just emergent, it's negotiable, a fluid construct that bends not just to gravity, but to the observer's very presence. The emergent time hypothesis flips the script on everything we assume about time's fundamental nature. Imagine standing in a crowded stadium, watching a wave ripple through the stands. It's not a physical object, but a pattern emerging from thousands of individual movements. Time, according to this theory, works the same way. It's not a backdrop to the universe, but a collective hallucination, a side effect of countless tiny interactions creating the illusion of flow. Physicist Julian Barber puts it starkly: time is nothing but change. In his vision, the universe is a vast mosaic of static nows, and what we perceive as time is just our brain stitching these moments together, like a flipbook tricking the eye into seeing motion. But here's the puzzle. If time is emergent, why does it feel so directed? Why do we remember the past but not the future? The answer might lie in entropy, the universe's tendency toward disorder. Think of a shattered glass. The pieces don't spontaneously reassemble because high entropy states are far more numerous than ordered ones. Our brains, wired by evolution to track cause and effect, mistake this statistical bias for the flow of time. It's as if we're drifting down a river, convinced the current is real, when in reality, the water's just following the path of least resistance. Yet some physicists push further, suggesting that entanglement, the quantum phenomenon linking particles across space, might be the hidden engine of emergent time. Picture two dancers perfectly in sync, their movements mirroring each other instantaneously. Now scale that up to every particle in the universe, their interactions creating a web of relationships so dense that it generates the illusion of a shared timeline. In this view, time isn't a river but a symphony, with each note's meaning defined by its relation to the whole. This brings us to the 13th theory's cosmic player, the observer. Quantum mechanics has long grappled with the role of consciousness in collapsing probabilities into definite outcomes. Could our very act of perception be what crystallizes time from the quantum fog? It's a controversial idea, but one that bridges physics and philosophy. If a tree falls in a forest with no one to hear it, does it make a sound? The emergent time hypothesis asks a sharper question. Without an observer, does the forest even have a when? The implications ripple outward. If time is emergent, could advanced civilizations manipulate it by engineering entanglement on macroscopic scales? Might there be regions of the universe where time emerges differently, faster, slower, or not at all? The answers remain speculative, but the questions alone stretch the imagination, revealing a universe far stranger and far more interconnected than we ever dreamed. Now consider this. If time is an illusion, what does that make us? Are we fleeting shadows cast by a timeless reality, or active participants in its creation? The next theory plunges deeper, suggesting that the answer might lie in the fabric of reality itself, not as a fixed stage, but as a dynamic, ever-evolving dialogue between observer and observed. The participatory universe theory doesn't just challenge our understanding of time, it upends the very idea of an objective reality. Imagine walking through a forest at night, flashlight in hand. The beam illuminates one patch of ground at a time, but does that mean the rest of the forest ceases to exist? John Archibald Wheeler's radical proposition suggests something similar. The universe only crystallizes into definite states when observed, like a cosmic game of 20 questions where every answer shapes the next question. Time, in this view, isn't a river flowing independently of us. It's more like a script being written in real time, with consciousness as the co-author. Wheeler's inspiration came from the double-slit experiment, where particles behave as waves until measured, as if reality hesitates until someone looks. Extend this idea to time, and you're left with a staggering possibility. The past might not be fixed until the present observes it. Think of old family photos fading in an attic. Do they only solidify into history when you uncover them? Critics argue this veers into philosophy, but quantum mechanics offers tantalizing clues. Delayed choice experiments show that particles can retroactively decide their path, as if future observations reach backward to mold the past. Yet here's the thorniest question. If reality requires an observer who observes the observer, some physicists sidestep this by proposing self-referential loops. Consciousness emerges from the universe, which in turn emerges from consciousness, like a snake eating its tail. Others suggest a cosmic democracy, where every interaction counts as an observation, from human scientists to collapsing stars. But the most provocative idea is that the universe might be a self-excited circuit, waking itself up moment by moment through its own participation. This isn't just abstract musing. If consciousness shapes time, could we engineer reality by changing how we observe it? Meditation studies hint that focused awareness alters subjective time. Could advanced civilizations tune time's flow collectively? The implications spiral outward, blending physics with existential wonder. Now consider the 14th theory, where speculation meets hard data. If the participatory universe feels untestable, quantum decoherence offers a measurable framework, a way to track how observation stitches time's fabric, one collapsed probability at a time. The line between witness and world might be thinner than we ever dared believe. Quantum decoherence pulls back the curtain on one of physics' greatest mysteries, how the fuzzy realm of quantum possibilities sharpens into the concrete world we experience. Picture a symphony tuning before a performance. At first, the notes are chaotic, overlapping, impossible to distinguish. Then, one by one, the instruments lock into harmony, and the music snaps into focus. That's decoherence in action, the process by which quantum superpositions, those ghostly states where particles exist in multiple places at once, collapse into the single, definite reality we perceive as now. The magic lies in interaction. Isolate an electron in a lab, and it can spin both clockwise and counterclockwise simultaneously. But expose it to even a single photon, and the superposition unravels, choosing a single state as if embarrassed by the attention. This isn't just lab behavior, it's how reality crystallizes moment by moment. Every collision, every whisper of heat, every gravitational tug acts like a cosmic photographer, developing the blurry quantum negative into a sharp classical print. Yet here's the twist: decoherence doesn't just explain the present, it hints at why time feels irreversible. Think of ink dropped into water. The dye spreads chaotically, and reversing the process is unimaginable. Similarly, once quantum information scrambles into the environment through decoherence, it can't be neatly gathered back. This one-way scattering might be the hidden engine behind time's arrow, turning quantum uncertainty into the steady drumbeat of cause and effect we take for granted. But the biggest question remains: what is the environment that triggers decoherence? If the universe began as a perfectly isolated quantum system, how did the first decoherence happen? The answer might lie in the 15th theory's cosmic conspirator gravity, not as a force but as a sculptor, bending the quantum stage until the actors have no choice but to pick a role. Imagine a dancer poised mid-pirouette, waiting for the stage to tilt beneath them. Gravity could be that tilt, the nudge that forced the universe to choose its first definite state, setting time's flow in motion. This isn't just theoretical sleight of hand. Experiments with massive molecules show that heavier objects decohere faster, as if gravity itself is impatient with quantum ambiguity. Could this mean that spacetime isn't just the stage for reality, but an active participant in shaping it? The implications are staggering. If gravity and decoherence are entwined, then time's flow might not be universal. It could vary with the density of matter, faster in galaxy clusters, slower in voids. And that raises a haunting possibility. If decoherence defines the now, could regions of the universe exist where it hasn't happened yet? Places where quantum fog still lingers and time hasn't truly begun. The boundary between these zones might be the most alien frontier of all, not a wall of fire or ice, but a shimmering curtain between reality and potentiality, where the universe hesitates unfinished. This brings us to the edge of the next theory, where gravity takes center stage not as a mere force, but as the architect of time itself. If decoherence is the brushstroke, gravity might be the hand that guides it, and the canvas could be far stranger than we ever imagined. The thermal time hypothesis turns our everyday experience of time into a cosmic mirage, an illusion conjured by the universe's relentless drive toward disorder. Picture a desert where heat shimmers distort the horizon, making distant objects appear to waver. Carlo Rovelli's groundbreaking idea suggests time works the same way. It's not a fundamental thread woven into reality, but a side effect of thermodynamics, rising from the dance of hot and cold like steam from a boiling pot. In this view, your wristwatch isn't measuring some universal clockwork. It's tracking entropy's subtle gradients, the silent friction as energy disperses. Think of a cup of coffee left on the counter. The heat slowly leaks into the air, and that irreversible slide from order to chaos is what we perceive as time's passage. Rovelli takes this further, arguing that without entropy change, without these thermal differences, time would simply vanish. It's as if the universe hit pause, freezing in a state where before and after lose all meaning. Even relativity, with its warped spacetime, fits neatly into this framework. Near a black hole where gravity bends light and slows clocks, entropy behaves differently too, as if time itself is just riding the thermal currents. But here's the paradox: if time is thermodynamic, what happens in a universe that reaches maximum entropy? Some models suggest time would effectively stop, like a wind-up toy winding down for good. Yet quantum fluctuations might stir the cosmic soup, creating pockets where entropy temporarily dips, restarting time's illusion in isolated bubbles. It's a haunting thought that time could flicker in and out of existence like embers glowing in the dark. This leads us to the 16th theory, where gravity steps in as the grand unifier. If thermal time explains the flow and relativity explains the curve, then quantum gravity might be the missing link, a framework where time isn't just emergent, but negotiable, bending not just to heat and motion, but to the observer's very presence. The boundary between these ideas isn't just a line in the sand, it's the frontier of physics itself. The relational theory of time tears down the idea of time as a universal clock ticking in the background of reality. Instead, it paints time as something far more intimate, a tapestry woven entirely from the relationships between events. Picture a bustling train station. The trains, the passengers, the arrivals and departures create a dynamic network of connections. Time in this view isn't the station itself, but the rhythm of interactions unfolding within it. Leibniz, the philosopher who first championed this idea, saw time as meaningless without change, like a clock with no hands, just an empty face. Einstein took it further, weaving relational time into relativity, where clocks tick at different rates depending on motion and gravity. The universe in this vision isn't a stage with a single timeline, but a chorus of rhythms, each tied to its own local events. But here's the puzzle. If time is just a web of relationships, what holds the web together? Gravity complicates the picture. Imagine two stars orbiting each other. Their motions define time for each other. But what about a distant observer? General relativity stitches these local times into a cosmic fabric, but the relational theory suggests something even more radical. Perhaps gravity itself emerges from the way events relate, like the tension in a spider's web arising from the connections between strands. It's a dizzying thought that the force holding planets in orbit might just be the sum of countless tiny relationships, each one a thread in time's invisible lattice. Now consider the implications for everyday life. If time is relational, then your experience of an hour spent waiting in line versus an hour lost in conversation isn't just psychological, it's a reflection of how densely events are connected in each moment. A boring hour feels long because few meaningful interactions occur, while a thrilling one flies by as relationships compound. Even memory fits this model. We don't recall uniform seconds but clusters of interconnected events like landmarks on a map. Yet the biggest mystery remains: what happens to time where nothing changes? In a perfectly static universe, no motion, no decay, no interaction, would time simply vanish? The relational theory says yes, like a dance floor emptied of dancers, leaving only silence. This leads us to the 17th theory, where time isn't just relational but negotiable, a fluid construct that bends not just to gravity, but to the very act of observation. If relational time is the web, the next idea pulls at its threads, revealing a universe where time isn't just connections, it's a conversation. Shape dynamics throws out the cosmic rulebook, declaring that space-time isn't the canvas of reality. It's just a fleeting shadow cast by something far more fundamental, pure geometry in motion. Picture a sculptor reshaping a block of marble, not by measuring inches or minutes, but by how the curves and angles relate to one another. That's the heart of this theory. Time isn't a universal river, but a local dance of changing shapes, where the universe's structure evolves without any fixed backdrop of space or duration. Julian Barber and his collaborators stripped physics down to its barest essence, revealing a cosmos where only the ratios between objects matter. A galaxy isn't here or there. It's a set of geometric relationships to everything else, constantly reconfiguring like a cosmic kaleidoscope. Now here's where it bends the mind. If time is just a gauge symmetry, a kind of mathematical bookkeeping for these shape shifts, then black holes become even stranger. In general relativity, a black hole's event horizon is a boundary in space-time, but in shape dynamics, it's more like a fault line in the geometry of relationships. Matter falling in doesn't just vanish, it rearranges the universe's underlying shape network, leaving behind a kind of topological scar. Think of it like cutting a knot from a tangled rope. The rope's overall structure changes, but there's no where or when the knot went, just a new configuration of twists. This could explain why black holes radiate Hawking radiation, not as particles escaping space-time, but as geometric echoes of the shapes that fell in. Yet the real shocker is what this means for the Big Bang. If time is emergent from shape changes, the singularity wasn't a point in time. It was a moment when the universe's geometric relationships hit a kind of reset. No before, no after, just a radical reconfiguration of ratios. It's as if the cosmos hit a cosmic Control plus Alt plus Del, rebooting into a new geometric mode. Critics argue this skirts the singularity problem too neatly, but supporters counter that it's the first theory to make the Big Bang feel less like a magical starting gun and more like a phase transition, like ice melting into water. This brings us to the 18th theory's even wilder terrain. If shape dynamics reduces reality to pure geometry, what happens when that geometry folds back on itself? The answer might lie in a realm where time isn't just local, it's optional, and the universe's blueprint can rewrite itself in ways that defy all intuition. The black hole time paradox isn't just a puzzle, it's a cosmic riddle that splits reality in two. Picture standing far from a black hole, watching a clock inch toward the event horizon. From your vantage point, time slows to a crawl, the clock's hands freezing like a broken watch. But for someone riding that clock into the abyss, time ticks normally, right up until the moment of no return. This isn't a glitch, it's a fundamental crack in spacetime's facade, revealing that what we call time might be nothing more than a cosmic sleight of hand. Einstein's equations predicted this eerie duality, but the implications are even stranger than he imagined. The event horizon isn't just a boundary, it's a hall of mirrors where time fractures into infinite reflections. For outsiders, matter falling in appears smeared across the horizon's surface like a bug trapped in amber. Yet for the infalling observer, there's no slowdown, no warning, just the inexorable pull toward the singularity. It's as if the universe has two sets of rules, and black holes force us to choose which one is real. This paradox isn't just theoretical. When the Event Horizon Telescope captured the first image of a black hole's shadow, it wasn't just seeing light bent by gravity, it was glimpsing time itself warped into a paradox. The glowing ring around the shadow, that's photons trapped in orbits where time loops back on itself, a visual echo of the chaos lurking within. Some physicists argue this isn't a flaw in our models but a clue. That spacetime is fundamentally holographic, with the event horizon acting as a cosmic hard drive, encoding information in two dimensions that our three-dimensional brains misinterpret as time's flow. Now here's the twist that bends the mind further. If time stops at the horizon from one perspective but flows normally from another, could black holes be stitching together different timelines? Imagine diving into one and emerging not in another place, but another when not through a wormhole, but because the very fabric of causality unravels at the edge. It's a wild idea, yet the math doesn't rule it out. Quantum mechanics suggests information can't be destroyed. So what happens to the time-stopped version of you that outsiders see frozen at the horizon? Some theories propose it's a hologram, a shadow cast into the future, while the real you plunges onward. This brings us to the 19th theory's even more tantalizing possibility, that black holes aren't just cosmic trash compactors, but portals to alternate histories where time's arrow splinters into infinite paths. If the paradox reveals anything, it's that space-time might be less like a stage and more like a script, with black holes as the places where the pages tear and the story rewrites itself. The ER equals EPR conjecture isn't just a string of letters, it's a revolutionary idea that blurs the line between quantum weirdness and cosmic architecture. Imagine two entangled particles forever linked across light years, their fates intertwined no matter the distance. Now picture that connection not as some abstract quantum glue, but as an actual bridge, a microscopic wormhole stitching space-time itself together. That's the heart of this theory. Einstein-Rosen bridges, those hypothetical tunnels through space-time, might be the physical manifestation of quantum entanglement, famously dubbed spooky action at a distance by Einstein, Podolsky, and Rosen. It's as if the universe built a hidden subway system where entangled particles aren't just communicating faster than light, they're shortcuts through the fabric of reality. But here's where it gets even wilder. If entanglement creates space-time tunnels, could we traverse them? The math suggests it's not impossible. Think of it like a quantum version of the classic sci-fi trope. Step into a portal here, emerge light years away. Except these portals wouldn't be glowing rings or swirling vortices. They'd be forged from the same eerie connection that lets two electrons mirror each other's spins instantly, as if sharing a single existence. The catch: these wormholes would be unimaginably tiny, fleeting, and unstable. Navigating one would be like threading a needle with a thread that dissolves at the slightest touch. Yet the implications are staggering. If entanglement is spacetime's hidden scaffolding, then time itself might not be the rigid barrier we assume. Particles linked this way could, in theory, share not just states but moments, creating bridges not just through space but across time. Picture a pair of entangled particles as bookends on a shelf, with a wormhole between them folding the timeline like a piece of paper. Suddenly, the paradoxes of time travel don't seem so paradoxical, just fiendishly difficult to engineer. This isn't just theoretical musing. Lab experiments with quantum teleportation already hint at the conjecture's plausibility, showing that information can leap between entangled particles without crossing the space between them. It's as if the universe is quietly admitting that yes, the shortest distance between 2 points isn't always a straight line. Sometimes it's a fold in the fabric of reality itself. Now let's push further into the unknown. If quantum connections can bend spacetime, could we one day harness them? The 20th theory dives headfirst into this question, exploring whether time travel isn't just a quirk of the math, but a future engineering challenge. Imagine a civilization advanced enough to weave entanglement into a network, not just for communication, but for navigation. A journey through such a system wouldn't be a leap into the unknown. It'd be a step into a web of relationships where every node is a doorway to another one. But before we get ahead of ourselves, there's a cosmic catch. The same quantum laws that make this possible might also enforce rules we can't break. Entangled particles might bridge spacetime, but manipulating them without unraveling the connection could be like trying to sculpt smoke. And then there's the grandfather paradox. If you change the past, do you sever the very entanglement that brought you there? The universe might have built-in safeguards, ensuring that while the threads of reality can twist, they can't snap. One thing's certain, the ER equals EPR conjecture doesn't just stretch our understanding of physics, it shatters the divide between the impossibly small and the unimaginably vast, revealing a cosmos where the quantum and the cosmic are two sides of the same coin. And if that coin has a third side, well, that's where the next theory takes us, into a realm where time isn't just traversable, it's optional. The Novikov self-consistency principle doesn't just regulate time travel, it locks it into cosmic handcuffs, ensuring every journey to the past was always part of history. Picture trying to rewrite a novel you've already read. Every edit you make was secretly there all along, woven into the story's fabric. That's the essence of physicist Igor Novikov's idea. If you travel back to prevent a disaster, your actions won't change the outcome, they'll be the outcome. The fire you tried to stop, your interference might be the spark that lit it. It's like a chess game where every move is both your choice and predestined, a loop where free will and fate dance in perfect, maddening sync. Take the infamous grandfather paradox. Under Novikov's rules, your attempt to erase your own existence would fail, not because time rebels, but because the universe subtly conspires. Your gun jams, your aim falters, a sudden noise distracts you. The cosmos becomes a meticulous editor, redacting contradictions before they're written. Think of it like a river flowing around a boulder. The water's path seems inevitable in hindsight, but only because every ripple adjusted to the obstacle in real time. But here's the twist that bends the mind further. What if some events are too chaotic to be neatly self-consistent? Enter the 21st theory, where time isn't a careful curator but a gambler rolling dice. Quantum mechanics already allows particles to exist in multiple states until observed. Could time travelers exploit this ambiguity, creating branches where paradoxes splinter into alternate timelines? Imagine stepping on a butterfly in the Cretaceous, not erasing the future but spawning a new one, while your original timeline rolls on unscathed. It's a cosmic shrug to Novikov's strictness. If reality can't enforce consistency, it might just multiply instead. The implications are staggering. Under self-consistency, time travel feels like walking a tightrope. One misstep, and the universe corrects you. But in a multiverse of infinite outcomes, every misstep builds a new tightrope. Suddenly, the past isn't a fragile relic but a playground of possibilities, where cause and effect aren't chains but seeds, sprouting forests of alternate histories. Yet this raises a haunting question. If time travel doesn't protect the past but fractures it, who or what decides which version you experience? The answer might lie in the observer's role, not as a passive witness but an active sculptor, chiseling reality from the quantum foam one decision at a time. And that's where the next theory takes us, into a realm where time isn't just traversable but malleable, shaped less by laws than by the very act of looking. The many interacting worlds interpretation takes the multiverse concept and cranks it up to 11, suggesting parallel timelines aren't just silent neighbors, they're constantly nudging each other, like rooms in a grand hotel where the walls are thin enough to hear whispers through the plaster. Unlike the traditional many worlds view, where branches split and never touch, this theory proposes that quantum vibrations might ripple between realities, creating subtle resonances that blur the lines between you and other you. Think of it like tuning forks set across a table. Strike one, and the others hum faintly in response. Could this explain those eerie moments of déjà vu, where a scene feels unnervingly familiar? Some physicists speculate these might be glitches in the cosmic matrix, fleeting overlaps where your consciousness brushes against another timeline's memories, like radio static bleeding between channels. But the implications run deeper than phantom feelings. If worlds interact, could information leak between them? Laboratory experiments with quantum systems already show particles behaving as if they're aware of multiple futures simultaneously. In this framework, that awareness might not just be internal, it could reflect faint gravitational handshakes with parallel versions of the experiment, each tugging on the others like invisible strings. Imagine a cosmic game of telephone where every decision you make sends faint echoes to alternate realities, and there's echo back, subtly shaping probabilities in ways we're only beginning to map. This leads us to the 22nd theory's even more tantalizing question. What if these interactions aren't random but patterned? Carl Jung's concept of synchronicity, meaningful coincidences that defy cause and effect, might find new life here. Could accidental meetings or uncanny timing actually be threads of resonance between worlds, moments when the universe's hidden harmonies rise to the surface? Picture two musicians in separate rooms improvising the same melody, not by design, but because the walls between them vibrate just right. Yet skeptics counter that without detectable energy exchange, these ideas flirt with metaphysics. But proponents point to quantum entanglement's spooky linkages as proof that influence doesn't always require force. If particles can sync across light years, why not realities across dimensions? The debate rages, but one thing's clear: the more we probe time's fabric, the less it resembles a solitary thread, and the more it looks like a shimmering web, trembling with every tug from every possible now. And that's where the line between physics and philosophy blurs. If time is a chorus of interacting worlds, then every choice, every chance event, might ripple further than we dreamed, not just branching futures, but bending them like wind-shaping dunes across infinite sands. The next theory dives into synchronicity's depths, asking whether these ripples could ever coalesce into something like cosmic rhythm, a hidden cadence beneath the chaos. The temporal landscape model doesn't just bend time, it turns it into a living, breathing dimension, pulsing and warping like the surface of a stormy sea. Imagine hiking through a valley where the distance between landmarks isn't fixed. Some stretches feel endless, others vanish in a blink. Now replace those landmarks with moments in cosmic history, and you've got a universe where time itself is stretchier in certain eras, denser in others. This isn't science fiction. Physicists like Lee Smolin suggest that just as gravity curves space, quantum fluctuations or dark energy might curve time, creating epochs where causality itself stutters or races ahead. Picture a clock buried in the early universe, ticking slower than its modern counterpart, not because of relativity's familiar speed or gravity effects, but because time's very fabric was thicker back then, like molasses compared to today's thin syrup. But here's where the real mystery kicks in. If time's flow isn't uniform across history, could the universe have forgotten stretches of its own past? Think of a record player skipping grooves. What if entire cosmic eras slipped through the cracks, leaving gaps in the fossil record of the stars? Some theories propose this might explain anomalies like the universe's missing lithium or the unexpected maturity of galaxies at the edge of observable space. It's as if time didn't just pass differently in those regions, it accumulated differently, like paint pooling in a canvas's crevices while other areas stayed dry. Now consider the implications for the far future. If time's landscape keeps shifting, could there come an epoch where causality unravels entirely? Imagine a river delta where channels split and merge unpredictably. Events might lose their logical sequence, with effects preceding causes in pockets of reality. The universe's fate wouldn't just be heat death or a big crunch. It could be a descent into temporal chaos where the very concept of before and after ceases to hold meaning. It's a haunting thought. That time, the scaffold of all experience, might one day crumble like a sandcastle in the tide. This leads us to the 23rd theory's even more radical proposition. What if time isn't just variable but optional in the universe's final act? As we peer into the far future, we might find a cosmos where time doesn't end. It simply fades from relevance, like a language no one speaks anymore. The stage doesn't collapse, the play just stops needing a clock. The big freeze isn't just an end, it's the universe exhaling its final breath. Picture a room where every candle has burned to its wick, every whisper faded to silence, and even the dust settles into perfect, motionless harmony. This is the fate cosmologists call heat death, entropy reaches its peak, all energy disperses into a uniform haze, and time itself becomes meaningless, like a clock frozen at midnight. Without temperature differences to drive change, stars won't just die, their ashes will stop swirling. Black holes will evaporate into faint ghosts of radiation. Even atomic motion will grind to a halt, leaving a cosmos so still. It's less like a graveyard and more like a photograph, eternally static. But here's the twist that keeps physicists awake. What if this isn't the end? Quantum mechanics whispers tantalizing possibilities. In a void where entropy reigns supreme, tiny fluctuations could still bubble up from nothingness, like ripples on a pond long after the stone was thrown. Given enough time, and enough here means numbers so vast they dwarf the age of our universe, one of these fluctuations might spawn a new Big Bang, rebooting reality from the ashes. It's as if the universe is a phoenix with feathers of pure randomness, waiting for the right quantum dice roll to ignite its rebirth. This isn't just poetic speculation. The math allows it. In an infinite timeline, even the most improbable events become inevitable, including the spontaneous birth of a new cosmos from the old one's corpse. Imagine a library where every book is the same blank page, until one day, by sheer chance, a single letter appears. Given eternity, that letter becomes a word, then a sentence, then a story. The big freeze might not be a full stop, but a semicolon, with the next chapter written in a language we can't yet decipher. Yet there's a darker alternative. If the vacuum of space isn't perfectly stable, if it's merely metastable, like a pencil balanced on its tip, then a single quantum hiccup could trigger a catastrophic phase transition. A bubble of true vacuum might form, expanding at light speed and rewriting the laws of physics as it consumes the cosmos. Time wouldn't just stop, it would shatter, replaced by something utterly alien. The universe wouldn't freeze, it would crystallize into a new form with rules we can't predict. This brings us to the 24th theory's fiery counterpoint. If the big freeze is the universe fading to black, the big crunch is its dramatic encore, a collapse so violent it rekindles the furnace of creation itself. Picture all galaxies reversing their flight, rushing backward into a singularity so dense and hot, it becomes the seed of another Big Bang. Time wouldn't just rebound, it would fold like an accordion, pressing the future into the past and birthing a new cycle from the wreckage. The difference between these two fates isn't just about endings, it's about whether time is a one-way street or a Mobius strip, looping back to start the story anew. The irony is exquisite. The same force driving the big freeze entropy might secretly sow the seeds of its own undoing. In the crushing densities of a big crunch, even maximum disorder could be scrambled back into order, like a deck of cards shuffled into perfect sequence by the sheer force of collapse. It's a cosmic paradox. The universe's slide into chaos could, under the right conditions, become the engine of its own rebirth. Now consider the ultimate question. If time can cycle endlessly, are we living in the first universe or the trillionth? The answer might lie in the next theory, where the fabric of reality isn't just reborn, it's rewritten, with each iteration tweaking the rules like a programmer refining code. The universe's final act might not be an ending at all, but a debug screen waiting for the next compile. The Big Rip doesn't just predict the end of the universe, it paints a portrait of annihilation so violent, even atoms won't survive. Imagine dark energy as a cosmic bully, growing stronger over time until it overwhelms gravity's grip, then electromagnetism's glue, and finally the very forces binding quarks together. Galaxies won't just drift apart, they'll explode into oblivion, stars wrenched from their orbits like beads from a snapped necklace. Planets will disintegrate mid-rotation, and in the final microseconds, your coffee cup, and the atoms composing it will vaporize into a spray of fundamental particles. Time itself won't just stop, it will be shredded like a calendar torn to confetti in a hurricane. This apocalyptic finale hinges on a sinister property of dark energy called the phantom divide, where its density doesn't just persist but increases as space-time stretches. Picture blowing up a balloon that never pops instead. Its rubber thins to nothingness, dissolving the balloon's very existence. The universe faces a similar fate. Expansion accelerates until the fabric of reality hits infinite stretch, a singularity where all distances become infinite in a finite instant. It's as if the cosmos is a piece of elastic pulled so taut, it ceases to be elastic at all. But here's the haunting twist. If the big rip is inevitable, could pockets of reality escape? Some theorists speculate about unbinding anomalies, regions where quantum fluctuations or hidden dimensions might resist dark energy's grip, like knots in a rope that refuse to fray. These cosmic lifeboats would be islands of causality adrift in a sea of fractured spacetime, their clocks ticking alone in the eternal aftermath. Yet even this grim scenario pales next to the 25th theory's audacious proposition that our universe is just one bubble in an infinite froth of multiverses, each with its own physics, its own time, its own fate. The Big Rip might be the end of our story, but the greater cosmos could be an endless library of tales, some ending in ice, others in fire, and some never ending at all. The real question isn't whether time dies, it's whether death itself is just a local phenomenon. The bounce cosmology doesn't just rewrite the universe's story, it turns it into an endless epic, where each chapter begins with a cataclysm and ends with a whisper. Imagine a cosmic pendulum swinging from a fiery Big Bang to a crushing Big Crunch, only to rebound again, over and over, in a rhythm older than time itself. This isn't just a cycle of destruction and rebirth, it's a grand reset where space-time itself crumples and smooths like paper in the hands of a relentless cosmic origami master. Time doesn't just pause between cycles, it reboots, like a computer powering down and restarting with a fresh operating system. But here's the mystery that keeps physicists up at night. If the universe resets, how does anything persist? How do the laws of physics remain so eerily consistent across cycles? Enter quantum memory, the theory that some imprint of the past lingers, etched into the fabric of reality like faint grooves on a vinyl record. Think of it as cosmic déjà vu. The universe doesn't remember its past lives in the way we do, but subtle quantum signatures might survive the collapse, whispering clues from one cycle to the next. It's as if the cosmos leaves fingerprints on its own rebirth, a hidden trail of breadcrumbs through the eons. The math behind this is as beautiful as it is bizarre. Quantum fields, those invisible scaffolds of reality, might retain faint correlations even as spacetime collapses. Picture a dancer spinning so fast they blur, but if you slow the film frame by frame, you'd see their arms and legs tracing patterns that persist despite the chaos. Similarly, quantum entanglement could tether information across the abyss between cycles, weaving threads of order through the firestorm of collapse. Some models even suggest that black holes, those cosmic vaults of information, might act as time capsules, their Hawking radiation encoding data that leaks into the next universe like a message in a bottle tossed between shores. Yet the implications stretch far beyond equations. If quantum memory is real, our universe might be haunted by echoes of its predecessors. The constants we take for granted, the speed of light, the strength of gravity, could be relics of an ancient tuning, refined over countless cycles until they landed in the sweet spot that allows stars, planets, and life to exist. It's a humbling thought that the laws we call fundamental might just be habits worn deep into the grain of reality by repetition. But skeptics raise a thorny question. If information survives, why don't we see evidence of past cycles? The answer might lie in the sheer violence of the bounce. The transition from crunch to bang isn't a gentle handoff, it's a blender set to cosmic puree, scrambling any coherent signal into noise. What survives isn't a detailed record, but faint statistical whispers, like trying to reconstruct a symphony from the static of a radio tuned between stations. This leads us to the 26th theory's even wilder frontier. If quantum memory bridges cycles, could consciousness itself be part of the carryover? Not memories or identities, but the raw potential for awareness, like a flame passed from one candle to another across the ages. It's a stretch, but not impossible after all. If the universe can remember the fine structure constant, why not the conditions that let matter dream? The bounce cosmology doesn't just offer an escape from the heat death of the universe. It redefines time as something both fragile and eternal, a phoenix that rises from its own ashes not by magic, but by the stubborn persistence of quantum whispers in the dark. And if those whispers are real, then every atom in your body might be part of a story older than existence itself, a story that's still being written, cycle after cycle, in the ink of spacetime's deepest secrets. The implicate order theory doesn't just hint at hidden layers of reality, it tears open the curtain entirely, revealing time and space as mere shadows cast by something far stranger. David Bohm's radical vision paints the universe as an infinite, enfolded tapestry, where every moment, every particle, is intricately woven into a deeper, implicate reality, like a hologram emerging from dimensions we can't perceive. Imagine dipping a piece of paper into ink, then folding it over and over until the original image vanishes. What's left seems random but unfolded, and the full picture snaps back into view. Bohm argued that time works the same way. Our linear experience is just one unfolded slice of a reality where past, present, and future coexist in a hidden wholeness. This isn't just poetic metaphor. Bohm's math suggests that quantum entanglement, those spooky connections between particles, might be glimpses of the implicate order's deeper logic. When two electrons sync instantly across light years, they're not breaking the speed of light. They're tapping into a layer where distance and separation are illusions, like characters in a movie realizing they're all just pixels on the same screen. It's a dizzying thought. The solid world we navigate might be a projection, with the true action happening offstage, in a realm where time doesn't flow but simply is. Now here's where it gets even wilder. If the implicate order binds all moments into one, could this explain precognition, those eerie flashes of future events? Bohm speculated that in the deeper reality, past and future might be as accessible as different pages in a book, with consciousness occasionally reading ahead by accident. Think of it like a radio picking up a faint signal from a distant station, not magic, just a temporary glitch in the tuning. Studies of presentiment, where subjects physiologically react to stimuli before they occur, tantalizingly hint at this possibility. Skeptics dismiss it as coincidence, but in Bohm's framework, it might be the universe's way of reminding us that time's arrow is just a local convention, not a cosmic law. Yet the most profound implication isn't about predicting the future, it's about redefining the present. If reality unfolds from the implicate order like a flower from a seed, then free will takes on new dimensions. Our choices aren't just reactions to a linear timeline, they're participations in a dynamic unfolding, where every decision ripples backward and forward through the hidden whole. It's as if we're not just actors following a script, but co-writers shaping a story that's already complete yet somehow still being written. This leads us to the 27th theory's even more startling proposition. That time isn't just layered, but fractal, with every moment containing infinite sub-moments, like a Russian nesting doll of nows. If Bohm's implicate order is the ocean, the next idea dives beneath its surface, revealing currents within currents, where the very fabric of causality might ripple in ways that defy all intuition. The retrocausality hypothesis flips our everyday logic inside out, suggesting the future might reach back to shape the past like a sculptor molding clay from both ends. Picture throwing a stone into a pond, except the ripples travel backward through time, influencing the moment the stone left your hand. This isn't just science fiction. It's grounded in the eerie results of delayed choice quantum experiments, where particles seem to decide their behavior retroactively based on measurements made after they've already traveled. It's as if the universe is a cosmic courtroom where the verdict changes the crime scene. Take the quantum eraser experiment, for example. Photons fired through a double-slit apparatus behave as waves when unobserved, creating an interference pattern. But if you later choose to measure which slit they passed through, even after they've already hit the detector, they retroactively collapse into particles, erasing the interference pattern as if rewriting history. The implications are staggering. The present isn't just shaped by the past, the future might be whispering to it too. But here's the paradox that keeps physicists up at night. If effects can precede causes, why don't we see time-reversed chaos everywhere? Why can't you stub your toe yesterday because of a decision you'll make tomorrow? The answer might lie in quantum safeguards, subtle constraints woven into reality's fabric to prevent paradoxes from unraveling causality entirely. Think of retrocausality as a river with gentle currents. Water can flow backward in eddies, but the overall current still moves forward. The universe seems to allow microscopic time loops while enforcing macroscopic order, like a strict editor permitting poetic license but vetoing plot holes. This delicate balance hinges on quantum entanglement's peculiar rules. When particles interact, their fates become intertwined across time as well as space, creating feedback loops that self-correct to avoid contradictions. Imagine two people writing a story together, one starting at the beginning, the other at the end. Their versions meet in the middle, and any inconsistencies are quietly resolved in the final draft. The universe might work the same way, with future and past negotiating a consistent timeline through quantum handshakes we're only beginning to decode. Now consider the ultimate mind bender. If retrocausality is real, could we one day harness it? Imagine sending signals backward to warn of disasters or optimize decisions, a cosmic undo button. The catch: any message sent would already be part of history, locked into a loop where cause and effect blur beyond recognition. You wouldn't be changing the past, you'd always have been part of it. It's a paradox wrapped in an enigma, revealing time not as a line but as a mosaic where every tile influences every other, no matter where it's placed. This brings us to the 28th theory's elegant solution: quantum safeguards that act as reality's immune system, isolating time-reversed effects to the subatomic realm while preserving the arrow of time we experience. Like a carefully coded algorithm, the universe seems to run checksums on causality, ensuring the books always balance even when entries are written out of order. The result: a cosmos where the future can nudge the past, but never shove it a dance of influence, not a free-for-all. And in that dance, we might finally find the rhythm of time's true nature. The transactional interpretation of quantum mechanics doesn't just play with time. It turns causality into a cosmic conversation where the future talks back. Picture tossing a pebble into a pond, but instead of ripples spreading outward, they surge backward too, meeting the initial splash in a perfect, self-reinforcing loop. That's physicist John Cramer's radical vision. Reality isn't built by particles moving forward in time, but by handshakes woven from waves traveling both directions, offers from the past met by confirmations from the future. It's as if the universe is a grand negotiation, where every event requires a deal struck across time itself. Take the double-slit experiment, where particles behave as waves unless observed. In Cramer's model, the particle doesn't choose a path when measured. It's the future detection event that sends a wave backward, sealing the agreement. The particle's behavior isn't a mystery. It's a transaction, like signing a contract where the terms are written in both directions. This explains quantum weirdness without parallel universes or collapsing wave functions, just echoes of what's to come resonating into the past, shaping the present into coherence. But here's the twist that bends the mind. If the future influences the past, who or what is the ultimate arbiter of these deals? Imagine a cosmic marketplace where buyers and sellers exist in different times, yet somehow agree on prices. The math suggests these transactions are self-selecting, like a jigsaw puzzle where only certain pieces fit together when viewed from both ends. A photon doesn't just happen to take a path. The path happens because the entire timeline, from emission to absorption, conspires to make it possible. It's not fate, it's a closed loop of mutual agreement where cause and effect blur into a single, shimmering knot. Critics argue this smacks of teleology, the idea that events are pulled toward predetermined ends. But Cramer counters that the model is mathematically equivalent to standard quantum mechanics, just reframed. The future isn't causing the past any more than your shadow causes you to stand in sunlight. It's all part of a unified process, like the two sides of a coin finally meeting at the edge. Now consider the implications for free will. If the future whispers to the present, are our choices illusions? Not necessarily. The transactional interpretation treats decisions as part of the negotiation, with consciousness acting as a participant in the handshake. Your now isn't predetermined. It's dynamically shaped by the interplay of past potentials and future confirmations, like a dancer improvising to music that hasn't finished composing itself. This leads us to the 29th theory's even deeper question. What if the observer isn't just a passive witness to these transactions, but the glue that binds them? Quantum mechanics has long wrestled with the role of measurement. Does observation create reality, or merely reveal it? The transactional interpretation hints at a middle path, that observers aren't outside the loop, but integral to the deal-making, their very presence completing circuits across time. It's as if reality waits for a witness to cosign its checks, ensuring the books balance in every direction, and that's where the line between physics and philosophy dissolves. If time's arrows are bidirectional, then the present might not be a point. It's a crossroads where past and future shake hands through us, the living witnesses. The universe isn't just happening, it's happening upon agreement, a dance of echoes where every step relies on the one before and the one yet to come. The digital physics hypothesis doesn't just reimagine the universe, it recasts it as the ultimate computer program, with time itself reduced to lines of code executing on some unfathomable cosmic CPU. Picture reality as a vast simulation where every particle's position, every star's glow, even your own thoughts, are just variables in an algorithm too complex for our minds to grasp. In this framework, time isn't a dimension, it's a processing queue, a step-by-step sequence where the universe updates its state, ticking forward like a grand cosmic clock cycle. But here's the twist. If time is computational, could it be manipulated? Imagine finding a glitch in the system, a buffer overflow in the fabric of existence. that lets you pause, rewind, or even rewrite the script. This isn't just speculative fiction. Physicists like Edward Fredkin and Stephen Wolfram have seriously explored the idea that the universe operates on discrete, rule-based computations akin to cellular automata. Think of Conway's Game of Life, where simple rules generate astonishing complexity. Now scale that up to reality. The laws of physics might just be the programming language of the cosmos, with time as the loop that iterates the simulation forward. Quantum indeterminacy, that's the universe's random number generator. Entanglement, a clever optimization to reduce latency between distant objects. Even black holes could be cosmic garbage collectors, compressing information into singularity pointers to free up memory. But the most chilling question isn't how the simulation works, it's why. Who wrote the code? Are we NPCs in some higher civilization's experiment? Or is the universe a self-bootstrapping AI, a program that spawned itself from nothingness? Theologians and scientists alike have wrestled with this, but digital physics adds a new layer. If we're in a simulation, the programmer might not be a who at all. It could be an ancestral universe running a historical reconstruction, or an alien child science project, or even a rogue AI testing infinite permutations of existence. The unsettling truth: we might never know. Any evidence we find could just be part of the simulation's lore, and that's where the 30th theory looms, the ultimate mystery. If the universe is code, what lies outside the runtime? Is there a base reality, or is existence an infinite stack of nested simulations, each unaware of the layers above? Some physicists argue that if simulating consciousness is possible, the odds favor us being in one of countless simulations rather than the original. Others counter that even simulated beings would perceive their world as real, making the question meaningless. But one thing's certain: if time is just a variable in the cosmic source code, then free will, destiny, even the arrow of time itself might just be clever illusions, side effects of an engine we're only beginning to reverse engineer. The irony is profound. We spend our lives racing against time, only to discover it might be as artificial as the ticking of a pocket watch. Yet in that realization lies a strange freedom. If the universe is a simulation, then every moment is both predetermined and precious, a unique state in an unfathomable calculation. Debugging reality might be impossible, but understanding its rules could be the closest we ever get to meeting the developer. And who knows, maybe the 30th theory isn't the end of the journey, but the prompt for a whole new query, one that even the simulation never saw coming. The panpsychist view doesn't just challenge our understanding of time, it redefines reality itself, suggesting consciousness isn't something the universe has, but what it fundamentally is. Imagine standing in a forest, not as an observer but as part of a vast, sentient network where every tree, every rock, even the wind carries its own flicker of experience. In this radical framework, time isn't an external force ticking away. It's the rhythm of this cosmic mind unfolding, moment by moment, like a dreamer's thoughts drifting from one scene to the next. Galileo and Descartes once stripped nature of its inner life, reducing the world to mere machinery. Panpsychism pushes back, declaring that even the smallest particles hum with a whisper of subjective experience, and time is the symphony those whispers create. Consider the humble atom. In classical physics, it's just a clump of particles obeying blind forces. But panpsychism asks, what if that atom feels its own existence, however faintly? Not with human thoughts or emotions, but with a primitive awareness of its own state, a quantum hum of being here now. Scale this up, and time emerges as the collective pulse of these experiences synchronizing, like fireflies blinking in unison across a dark field. The past isn't gone, it's the universe remembering itself. The future isn't unformed, it's the universe imagining what comes next. This isn't just poetic speculation. Modern iterations of panpsychism, like integrated information theory, propose that consciousness arises from the complexity of a system's interconnectivity. A brain has rich, layered networks, so it generates vivid human awareness. A rock's simpler structure might produce only a dim, fleeting sense of isness. But crucially, something is still there. Time then becomes the dance of these nested experiences, from the quark's quantum flutter to the galaxy's slow spin. It's as if reality is a vast chorus, with each voice singing its own note, and time is the melody that emerges when we listen to the whole. Now, here's the breathtaking twist. If consciousness is universal, whose dream is the universe, some traditions from Hindu cosmology to certain quantum interpretations suggest the cosmos might be a single, self-reflective mind, fragmenting into countless perspectives to explore its own depths. Think of it like a lucid dreamer spawning characters, each believing they're independent until they wake up and realize they were the dreamer all along. In this view, your sense of now isn't just your brain's computation, it's the universe experiencing itself through you, one frame at a time. But skeptics bristle. If rocks are conscious, why don't they write poetry? Panpsychists counter that consciousness isn't all or nothing, it's a spectrum. A thermostat might know temperature as a bare sensation, while a human knows the ache of nostalgia or the thrill of discovery. Time, then, isn't uniform either. A mayfly's brief life and a redwood's millennia might feel subjectively similar, their inner clocks stretching or compressing to fit their scale of existence. This brings us full circle to our first theory, the block universe, with a startling reconciliation. If all moments exist eternally in the cosmic mind, then time's flow might be how consciousness navigates that frozen landscape, like a flashlight moving across a darkened mural, illuminating one piece at a time. The universe isn't just a static sculpture, it's a sculpture that experiences itself being unveiled. The implications ripple outward. If time is consciousness unfolding, then death isn't an end but a reintegration, a drop returning to the ocean of awareness. Near-death experiences, with their reports of timelessness, might be glimpses of this deeper reality. Even quantum indeterminacy finds new resonance. Particles choose states because some rudimentary awareness leans toward one possibility over another. Ultimately, the panpsychist view doesn't just stretch the mind, it dissolves the boundary between mind and world. Time isn't a river we're swept along, we're the river and the banks and the sky reflected on its surface. The dreamer and the dream are one, and every tick of the clock is another stroke of the universe's brush on the canvas of itself. From the block universe to panpsychism, these 30 theories peel back the layers of reality like pages in a cosmic mystery novel, each one revealing space and time to be more fluid, more paradoxical, and more astonishing than we ever dreamed. Whether you're drawn to the frozen landscapes of Eternalism, where every moment exists simultaneously, or the shimmering holograms of the Implicate order, where time is just an unfolded slice of something deeper, one truth emerges: the universe refuses to play by our everyday rules. It's as if we've spent centuries studying the surface of a pond, only to discover the water isn't even wet, it's a projection from a dimension we can't see. Think about what this means for your own life. That moment you're living right now, it might already be etched into the fabric of space-time, or it could be one of infinite branches in a multiverse, or even a fleeting computation in some vast cosmic program. The theories we've explored aren't just abstract puzzles, they're invitations to see reality differently. Imagine waking up tomorrow with the certainty that time is an illusion, or that every choice you make spawns new universes? Would you live differently? Would the weight of a deadline feel lighter, or the beauty of a sunset feel richer? Here's the real magic: none of these ideas cancel each other out. The block universe's frozen eternity might coexist with the participatory universe's collaborative now. Quantum retrocausality could dance with the holographic principle, and panpsychism might whisper through the cracks in digital physics. The universe, it seems, is a master of holding contradictions, of being many things at once, much like our own minds when we dream. So which theory speaks to you? Maybe you're captivated by the elegant brutality of the Big Rip, or the poetic cycles of bounce cosmology. Perhaps the transactional interpretation's cosmic handshakes feel oddly comforting, or the idea of time crystals, matter that dances to its own eternal rhythm, fills you with wonder. Whatever resonates, remember this: the goal isn't to find the right answer. It's to keep asking better questions. The adventure doesn't end here. Hit subscribe to join us as we dive deeper into the mysteries of black holes, quantum entanglement, and the hidden forces shaping reality. Drop your favorite theory in the comments. We'll tackle the most intriguing ones in future videos. After all, the universe didn't put these puzzles in front of us to solve alone. Let's unravel them together. Until next time, keep looking up and never stop wondering what else might be hiding in plain sight. Imagine a quantum computer that doesn't just calculate faster, it reaches backward through time to optimize its own operations before they even begin. This isn't science fiction, it's the staggering potential of retrocausality applied to technology. Researchers are already exploring how quantum particles making decisions based on future measurements could revolutionize computing. Picture an algorithm that iteratively improves itself by sending feedback loops into the past, refining its code with each cycle until perfection emerges from what looks like magic. The implications are dizzying: medical simulations that self-correct errors before they happen, or climate models that incorporate data from future observations to pinpoint precise interventions. Now shift gears to holographic storage, but not the kind we've seen before. What if we could encode information not just in three-dimensional space, but in the very fabric of time itself? The holographic principle suggests reality might be a projection from a two-dimensional surface. Apply that to data storage, and you're looking at systems where entire timelines are preserved like layers in an onion. Imagine archival libraries that don't just store documents, but the entire history of their revisions, accessible by rewinding the storage medium to any moment in its existence. Museums could preserve artifacts not as static objects, but as dynamic processes, letting visitors experience ancient tools being crafted or paintings evolving stroke by stroke. But the real game changer lies in energy. If time crystals, those bizarre quantum structures that oscillate without energy input, can be scaled, they might unlock perpetual motion at the atomic level. Think of a smartphone battery that doesn't degrade, or a satellite that adjusts its orbit using time crystal rhythms, harvesting entropy like a windmill catches breeze. The catch: these technologies would operate outside classical thermodynamics, bending what we thought were unbreakable laws. It's like discovering a hidden cheat code in the universe's operating system. Then there's the wild card: gravitational wave computing. If space-time is as malleable as relativity suggests, could we engineer chips that process information by rippling the fabric of reality itself? Data wouldn't travel as electrons but as distortions in space-time, with calculations happening at the speed of thought, literally. A single such processor could solve problems that would take conventional supercomputers longer than the age of the universe, from cracking unbreakable encryption to simulating the birth of multiverses. Yet the most profound impact might be on human consciousness itself. If panpsychism holds even a grain of truth, future interfaces could tap into the latent awareness of particles, creating biocomputers that think in ways we can't fathom. Imagine a medical implant that doesn't just monitor your heartbeat but senses your body's quantum fluctuations, predicting illness before symptoms arise by listening to the whispers of your cells. The line between physics and engineering is blurring, and the next generation of breakthroughs won't come from incremental upgrades. They'll spring from these radical reimaginings of reality's rules. The theories we've explored aren't just intellectual exercises, they're blueprints waiting for builders. Whether you're a coder, a biologist, or an artist, the tools to shape this future are within reach. The universe has handed us its deepest secrets. Now it's our turn to build with them.